Hello everybody, welcome to the lecture series Foundation for VLSI Design. I am Sneh Saurabh, Associate Professor, IIIT, Delhi. Before starting this lecture series, let us understand that what this lecture series is all about. So the objective of this lecture series is to revise fundamental concepts necessary to master topics related to VLSI design. Note that the objective is to revise the fundamental concepts. So we are assuming that these you are already introduced to these fundamental concepts in your earlier courses, and the purpose of this lecture series is to revise those concepts. And why we are revising these concepts? So the reason is that these fundamental concepts are heavily used in advanced courses such as VLSI design flow, and therefore you must be very much thorough in these concepts. And this lecture series has been created so that you can revise and become thorough in the concepts before you head to the advanced courses in VLSI design. So what are the topics that will be covered in this lecture series? So this lecture series is divided into 10 lectures, and in the first 5 lectures we'll be looking into the fundamentals of digital systems. And then we'll be briefly looking into semiconductor devices and especially MOSFETs. And then we'll be looking into CMOS inverters, because the CMOS technology is the most widely used technology in the semiconductor industry. And then we'll be briefly looking into the algorithms and data structures, which are also very important for VLSI design. So let us start with the first lecture on digital system. In this lecture, we'll be discussing the topics digital signal. Then we'll be looking into that why digital systems are more resilient, and what are binary numbers, and what is a few concepts related to Boolean algebra. Now, what is a digital system? A digital system is a system which manipulates digital signals, and therefore we must understand that what is a digital signal. Now, before understanding the digital signal, we should note that the natural signals are analog signals. For example, the natural signals can be variation in pressure. For example, the sound is a variation in pressure, and similarly there can be light intensity variation, those are optical signals, or temperature variations, which are thermal signals. So these signals are analog signals, and we need to basically derive digital signals from the analog signals. And how do we derive the digital signals from analog signals? So we convert first the analog signals, which can be in various form of energies, such as it can be the sound energy or light energy or heat energy. So first we convert the analog signals, which could be in other forms of energy, to an analog signals which is represented electrically. These electrical analog signals could be variation in electrical quantity, such as voltage or current. And how do we convert these analog signals to electrical analog signals? So we use a device which is known as transducer. So transducer is basically converting the signal from one form of energy to electrical energy, right? For example, if we say we consider the audio signal, for example, as I speak, so the sound waves, it is translated, or the sound energy is basically is changed to an electrical signal with the help of a device which is the microphone. So microphone in this case is a transducer. So given an analog signal, with natural signal, which could be in the form of an audio signal or optical signal or thermal signal, we use a transducer, for example a mic or a camera, to convert that analog signal to an electrical analog signal. And then we convert the electrical analog signal to a digital signal with the help of a device which is known as analog to digital converter. Right? Now, how does an analog to digital converter converts an analog electrical signal to a digital signal? So it carries out two important processes. The first is sampling at discrete time instant and quantization. So let us understand what is sampling at discrete time instant and quantization. Now let us understand how does an analog to digital converter converts an analog electrical signal to a digital signal. So the first thing that the analog to digital converter does is it samples. It samples the analog signal at discrete time intervals. For example, suppose this is the analog signal which is shown here. It is varying continuously with time, right? So the value of this analog signal is sampled at discrete time instance 1, 2, 3, 4, 5, and so on. So the values of the analog signal is not sampled continuously but only at discrete time intervals. And then after sampling, what analog to digital converter will do is the quantization. So it will represent the value of the analog signal using a discrete set of values, right? So the amplitude of this analog signal is varying continuously, right? In the range from 0 to 7, it is varying within this range. It is varying continuously, right? The amplitude is varying continuously. But analog to digital converter will not represent a continuous value. It will represent the amplitude using a discrete set of values. In this particular case, the discrete set of values are 1, 2, 3, 4, 5, 6, 7, right? So if the signal is between say 6 and 7, right? For example, this point. So it is represented here in this case as 7, right? Similarly, if we see that at any particular value, for example, in this case here, right? So in this case, the value is between 5 and 6. So the value, the analog to digital converter, what it will do is that it will represent the value not as say 5.2 or 5.3, which may be the exact value of the analog signal, but it will represent using discrete set of values. In this case, it is closer to 5, so it will be represented as 5 rather than 5.2, right? So when an electrical analog signal is given to an analog to digital converter, it will sample and do quantization, and at the end we'll get a digital signal. So digital signals are represented as a sequence of bits 0, 1, right? For example, in this case, the value, for example, was 5. The value at this point was 5. So it will be represented as a sequence of bits, right? So it will be represented as 1, 0, 1, meaning that the number 5 is a decimal representation of the number, but we will convert it into a binary number, and it will be represented as 101, right? So digitals at the end of at the end, when we get a digital signal, will get only a sequence of the zeros and ones, right? Now let us look into the functionality of an analog to digital converter in some more detail. So analog to digital converters are also known as ADCs in Sure, right? So in an analog to digital converter, the full analog signal range is divided into a finite number of discrete values, right? And then given an analog signal, the amplitude of that analog signal is mapped to appropriate discrete value within this range, right? So let us understand it with the help of an example. Suppose there was an ADC whose full range was 0 to 1 volt, right? So the minimum voltage was 0 volt and the maximum voltage was 1 volt, right? So the lowest volt, assume that this ADC produces a digital signal with 8 bits, right? So the lowest voltage, that is 0 volt, will be mapped to all zeros, and the highest voltage 1 volt will be mapped to all ones, right? And any voltage between these two range will be represented appropriately by a sequence of zeros and ones using 8 bits, right? So now given this ADC, what will be the analog voltage range per bit, right? For example, suppose the voltage was 0 volt, and if we want to increase it to say 0001, this, right, by we change the lowest bit from 0 to 1, right, then how much voltage will be required? So the voltage required will be 1. So first we should understand that how many discrete values will be there between 0 to 1 volt, right? So since we are representing the amplitude of the analog signal using 8 bits, the values that are possible are are 2 to the power 8, right? Meaning that each of these 8 bits can either take 0 or 1, and there are 8 bits, so there will be 2 into 2 into 2, that is 2 to the power 8, right? So these many possible values are possible, right? 2 to the power 8 is nothing but 256, right? So within the 0 volt to 1 volt, we can have 256 volt, 256 values, right? And therefore the analog voltage range per bit will be nothing but 1 volt, that is the range, full range of this ADC, 1 volt divided by 256 possible values, that will be around 3.9 millivolt. Now if we want to make this analog to digital converter more sensitive, what can we do? The simplest thing would be that we can increase the number of bits in the representation of the digital signal. So the accuracy can be improved if we use 10 bit, for example, instead of 8 bit, right? So if we increase the number of bits in the ADC from 8 bit to 10 bit, then what will be the analog voltage range per bit in this case? So it will be, since there are 10 bits, now between 0 volt to 1 volt, there will be 2 to the power 10 or 1024 values, right? And therefore the number of the analog voltage required for 1 bit of change, right, one from between two consecutive discrete values, the analog voltage change required will be 1 volt divided by 1024, that will be 0.98 millivolt, right? So instead of using 8 bits, if we use 10 bits, then the voltage range per bit, analog voltage range per bit reduces, and therefore the accuracy of the ADC will increase, right? So just to summarize, how do we get a digital signal, or we get digital signal from the analog signal using transducer and analog to digital converter, and the analog to digital converter produces a digital signal whose accuracy accuracy can be improved if we increase the number of bits in the representation of the digital signal. Now, once we have got this digital signal, so we saw that the digital signal is nothing but a sequence of zeros and ones. And these sequence of zeros ones can be so these digital signals are represented in binary number system rather than decimal number system. So let us understand what are binary numbers. First, let us understand that what is the decimal number system. So we are all familiar with the decimal number system. So in a decimal number system, we use 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So decimal number consists of these digits only, right? So decimal number is said to be in base 10. 10 digits are used. For example, if we consider a number 5723, right? So this number 5723 basically represents the in this representation, the place value of each digit is in powers of tens. For example, this 3, what is the what is the place value of this, right? So the place value of this digit is 10 to the power 0, that is 1, right? Then what is the place value of 2? It is 10 to the power 1. What is the place value of 7? It is 10 to the power 2. And what is the place value of 5? So it is 10 to the power 3, right? So in the decimal number system, we have the place value of each digit is in powers of tens. Now let us understand what is a binary number. So in a binary number consists of only digits, zeros and ones, right? Instead of 10 digits, we can have only two types of digits, zeros and ones, right? So binary number is said to be in base 2 and two digits are used. For example, if we consider a binary number 1001, right? Now in this case, place value of each digit is in power of 2, right? So for example, the place value of this first one is 2 to the power 0 or 1. Then the second 2 is 2 to the power 1, right? The third 2, it is 2 to the power 2, right? Or that is 4, right? And the place value of the last one is 2 to the power 3 or 8, right? So we can see that 1001, if we want to represent it in decimal number system, it will be 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 0 into 10 to 2 to the power 1 plus 1 into 10 into 2 to the power 0, right? That is 9, right? So the analog, the digital number, sorry, the binary number system is very much similar to the decimal number system. Only thing we should note here is that instead of 10 possible digits, we'll have only two possible digits, that is 0 and 1, right? So why are actually we use this binary number system in digital system? So in digital system, we represent digital signals using binary numbers. So there are many reasons why we want to use binary numbers in for a digital system. One of them is that it can be conveniently represented by as two voltage levels, right? For example, 0 we can represent it as 0 volt and 1 we can represent it as 1 volt, right? So we can easily represent 0 and 1 using two different voltage levels, right? So the representation of the number in an electrical form becomes much easier if we use a binary number system. The other important thing is that it is very easy to process the binary numbers, right? Because there are efficient circuits, for example, adders, subtractors, multipliers, and so on, which works on very efficiently on binary number system, and therefore we typically implement digital system using binary or we use binary number systems in digital systems, right? And there are other important reasons that we use binary numbers to represent digital signals. So let us look at one of the most important reason for using binary numbers in a digital system, and that is related to the robustness of the digital signals. So we have seen that digital signals are represented using binary digits or bits, right? For example, we saw that we can represent an analog signal to in as a digital signal as sequence of bits which are generated by the analog to digital converter, right? And we can represent these digital signal which are sequences of zeros and ones using voltage levels. For example, we can represent 0 or 1 as supply voltage VDD, or supply voltage VDD can be used to represent the digital can represent the binary digit 1, and 0 volt or ground can be used to represent the binary digit 0, right? And in addition to this, there is something more which leads to robustness in the digital signal or digital system, and that is related to the margins. So we add margins to the voltage levels in the interpretation of the logic values. For example, suppose we consider 1 not only when the voltage value is VDD, but any voltage in the range, say V1 max to VDD, that is within this range, will be considered as 1, right? So it is not only a particular value VDD which is considered 1, but the entire range of voltage between this V1 min to VDD, right? That will be considered as a logic 1. Similarly, we not only consider the values ground voltage as logic 0, but any voltage between 0 volt to V0 max, that will be a considered as a logic 0, right? So what happens is that because of this addition of margin in the representation, we can we can have an intermediate values also, and that will be represented or interpreted and or manipulated by the digital system correctly. For example, let's say that the VDD was 1 volt and V1 min was 0.8 volt, right? So any voltage between 0.8 volt and VDD was 1.2 volt. So anything between 1.2 volt and 0.8 volt, that will be considered as logic 1. And anything between 0 to zero point 0.5 volt will be considered as logic 0. This is one way of defining the bits or logic 0 and logic 1, right? So suppose this was the representation. So in this representation, what will be the value of 0.9, right? So the 0.9 will be somewhere here between 1.2 and 0.8, and therefore it will be represented as logic 1. And if it was 0.3 volt, it will be it falls between 0 volt and 0.5 volts, and it will be represented as 0. So the digital system have margins where it can tolerate the voltage levels, right? So between 0.8 and 1.2 volt, that is it has got a margin of 400 millivolt for the logic 1. Similarly, from 0 to 0.5 volt or 500 millivolt, between this range, between in this 500 millivolt interval, there can be logic 0, right? So this margin allows the digital system to work more robustly, right, compared to a purely analog system. So there is a margin for error, and this makes digital system robust or immune to noises, and designing it becomes more flexible and easier, right? So even if, say, suppose the voltage was, say, 0.9 volt, and there was some noise in the system. The noise can be thermal noise, or the noise could be because of many other reasons, and this voltage shifted from, instead of the design value of 0.9 volt, it became say 0.95 volt, or it became a 0.85 volt. Then still it falls within the range VDD to V1 min, and it will be correctly represented as logic 1, right? And therefore there is a margin for error which allows the digital system to be more immune to the noises, and also designing becomes easier, because if there are margins in the interpretation of the digital or voltage levels, then a designer can be more relaxed in choosing the voltage levels for the system. Now let us look briefly into Boolean algebra. So digital circuits operates on bits or binary digits, and we can design and analyze digital circuits using binary Boolean algebra. Now, what is a Boolean algebra? So in Boolean algebra, we have Boolean variables, right? Boolean variables are those variables which can take either value 0 or 1 and nothing else, right? And there are two basic operations defined on the Boolean variables. And what are these basic operations? And or, right? These are the two basic operations. And what is the definition of and? So and, which is also known as product or conjunction, it is defined or it is denoted as dot, right? So we write A dot B means that there is an operation of and between A and B, right? Some shorthand notation, we also write AB to denote that this is an and of two Boolean variables A and B. Now, what is the definition of the and operation? So if we say that we are doing an and operation of A and B, then the result will be 1 if and only if A is equal to 1, B is equal to 1, and in no other cases, and in other cases the value will be 0, right? So this is the definition of the and, right? And for the AND operation, the identity element is 1, meaning that A and 1 will always be A, right? So the identity element retains the original variable. So A dot 1 is A, right? Now what is an OR operation? So OR operation is also known as sum or disjunction, and it is denoted by plus. So A plus B is 0. So A and B are Boolean variables. A plus B is 0 if A is equal to B is equal to 0, and it is 1 in all other cases, right? And what is the identity element for the OR operation? So the identity element is 0. So A plus 0 is always A, right? Besides this and OR operations, there is also a complement. And what is complement? Complement of A is denoted as A dash, and taking or it is also called taking complement or taking and not doing a not operation. So what is the definition of complement? So if A is 0, then A complement is 1, right? And if A is equal to 1, A complement is 0, right? So this is the definition of the complement. So these are the basic operations defined on the Boolean variable in Boolean algebra. Now we can form Boolean expressions in Boolean algebra. We can form Boolean expression using Boolean variables, constants, the constants are zeros and ones, and Boolean operators and, or, and not, right? For example, A plus B dot C bar or C dash plus E F, right? E dot F, that is the product. So we are taking here the sum, then we are taking product with the complement. C dash is complement, right? The precedence of this operator is not, then and, then or. And if we want to override this precedence, we can use parenthesis, right? Parenthesis to specify the order of operation explicitly in a Boolean expression, right? Now let us look at a few important properties in of Boolean algebra. So the addition, or the addition, a plus b is equal to b plus a, that so the addition is and multiplications are commutative, that is a plus b is equal to b plus a dot b is equal to b dot a, and this addition and multiplication or are or operation and operation are also associative, that is a plus b plus c is same as a plus b plus c, right? And then a dot bc is equal to ab dot c, right? So these are associated. Then this addition, as the and the or operation are distributive. And then we also have the absorption property, right? So a plus a dot b is same as a, and a dot a plus b is same as a, right? And then there is a De Morgan's theorem, and this is very important because this leads to many simplification which are typically widely used or often used in designing digital system. So a plus b whole complement is equal to a complement dot b complement, right? And a dot b whole complement is equal to a complement plus b complement, right? So these are two De Morgan's theorems. So now, before ending this lecture, let me on a lighter note, let me ask you to read this statement aloud. And if you haven't able to read this statement correctly, then I think your way of thinking and of a digital system or a computer is the same. And these are some of the references that I've used in preparing these slides. So to summarize in this lecture, what we have done is that we have looked into the digital signal and what is a digital system. We looked briefly into what are binary numbers and briefly into Boolean algebra. So in the next lecture, we'll be continuing with the digital system. Thank you very much.